Hi, I'm Rob Picard, and this is my submission for Revolution Prep. It's called The Photoelectric Effect, Einstein, and the Discovery of Quantum Mechanics. Now, around the turn of the last century, there was a serious problem in physics. Basically, science moves along when there are experiments which can test a new theory, and theories which can explain new experiments. In 1900, there was an experiment for which the classical theories of light did not work. They failed, and that experiment was called the photoelectric effect. Basically, classical theory states that light is essentially a wave and that it is continuous in nature. All of the physics of waves, such as diffraction and interference, apply. But the photoelectric effect was an experiment for which these classical wave-like theories did not apply. And let me go ahead and describe to you how the apparatus worked and what went wrong and why it wasn't understood. So here is the photoelectric effect apparatus, and this is a glass enclosure with a vacuum in it, okay, and that inside there is a piece of metal called an emitter, and the metal emitter is surrounded by a metal cup called a collector. The bottom of the glass enclosure has a quartz window over here, and then incident light comes through the quartz window and it hits the emitter. It's going to release some electrons, which we call photoelectrons, which then fly through the vacuum here and then hit the collector. And that forms a current which can be measured. Now, it's possible to actually control the speed of the photoelectrons coming out of the emitter to the collector using a variable voltage. Basically, you put a voltage or a potential between the emitter and the collector, and you can either speed up, slow down, or even stop completely the electrons coming out of the emitter to the collector. So that's basically how it works. Now, the experiment is trying to understand how light interacts with a metal surface and the electrons in it, but it was not understood at all, and the wave theories of light did not work well for the photoelectric experiment. So I'm going to go back to the apparatus here and explain what went wrong and why it wasn't understood. First, it was found that no matter what the intensity of the illumination of the incident light, that's here, reaches the emitter, the kinetic energy of the photoelectrons did not change. But classical wave theory suggests that the higher the illumination, the greater the kinetic energy, so this didn't work. Second, according to wave theory, the photoelectric effect should occur for any wavelength of this incident light, or color of incident light coming and hitting the emitter. But the experiment found that there is a cutoff frequency, and below the cutoff frequency there is no photoelectric effect at all. That is, no photoelectrons came out of the emitter and hit the collector. And third, if light is a wave, an electron in the metal would receive only a small portion of the energy due to its small size, small surface area, so that there should be a time lag between the time that the incident light hits the emitter and the photoelectronics coming out of the emitter toward the collector, and no time lag was observed. So these were some three serious objections to the classical theory. So it led people to think in new directions, and what happened was in 1905, Albert Einstein made a new assumption about the nature of light, namely that light behaves as if it's concentrated into bundles called photons. So let me show you a little bit about Einstein's theory here. Basically, Einstein postulated that energy came in bundles, E, which are equal to H. H is a constant called Planck's constant. All that is a number times the frequency nu. So E equals H nu as a bundle of energy in a photon. In the photoelectric effect, H nu, that's a photon, is equal to phi, that's the work function. The work function is the energy it takes to get the electron out of the atoms of the metal and flying into free space, plus K max, and K max is the kinetic energy of the fastest photoelectron coming out of the emitter to the collector. So that was what Einstein came up with. Now, his revolutionary hypothesis satisfies all of the objections of the wave theory and the photoelectric effect. Now, the first objection was that, let me bring back the apparatus here and I'll show you how it worked. there is a total lack of dependence of the intensity of illumination here on the kinetic energy of K max. That's the photoelectrons leaving the emitter and going to the collector. Einstein's theory is in total agreement with the finding of the photoelectric effect. If you double the number of photons in the light, that is, the intensity is increasing, and so therefore the number of photons increasing, every individual photon is still below the energy it takes to get the photoelectron out of the from the emitter to the collector. So score 1 for Einstein. Now, if K max is equal to 0, so that we have h nu is equal to phi, there is just enough energy for the electron to escape the work function, so we have no kinetic energy at all. If the frequency is below the cutoff frequency, then each photon will simply lack the energy to overcome the work function and release the photoelectron. That's entirely in agreement with the experiment, so score 2 for Einstein. And third and lastly, there is no time lag from the time the illumination begins to the time the photoelectric current begins, because the photon energy is in a concentrated bundle and not spread out over a wave. So score 3 for Einstein. Now, the photon theory of light was a triumph because it ushered in a new understanding of light. Much of modern technology, including the laser and the integrated circuit, relies on this understanding. So that's my presentation. I'm Robert Picard. Thank you.